Hello everyone, welcome to the 20th episode of the series. In this video, we'll talk about properties of linear transformations. So last time, we learned about the linear transformation of a given matrix A, and we saw a few examples. We also saw the example of a non-linear transformation, and that was translation. So today, as I said, we're going to explore linear transformations a little bit more. But before we get there, uh, I want to review the idea of a function. So a function in mathematics is a rule for taking in an input and then returning an output. So you could also think of a function as a machine that takes in a particular input and gives out an output. So when we define a function, there is of course this rule or this assignment that I just mentioned, but we also have two sets in the definition. The first is called the domain, and that's the set of all allowed inputs. And the other thing is the set of all possible outputs, which we call the codomain. We can also give like the function a name, and we can write like a given function as an assignment from the domain to the codomain, and we read it out aloud as f from A to B. And we also call functions sometimes maps, operations, or transformations. So let's look at a few examples. In the first one, we're given the function f of x equal to x squared plus 1. So this function inputs numbers and outputs numbers as well. Its domain is the set of all real numbers, and its codomain is also the set of all real numbers. So for every input x, the output is 1 more than the square of x. So if you send in a 3, your output is going to be 1 more than the square of 3, which is then 10. Similarly, in the second example, rotating a vector in the plane by 90 degrees counterclockwise is also a function, but with domain R2 and codomain R2 as well. So what this does is it takes any vector and it assigns it to a vector, which is the 90-degree rotation counterclockwise of it. So for example, 1, 2 will get mapped to minus 2, 1. In other words, if 1, 2 is the input to this rotation function, the output will be minus 2, 1. In the last example, we have this function which is the derivative function or the derivative operation. So the input is always going to be a differentiable function, and the output is going to be the derivative of the input. So for example, if I input x squared plus 1, its derivative is going to come out as the output. So let's come back to linear transformations. Recall that for any given m by n matrix A, we have a linear transformation TA from Rn to Rm. What this means is that the domain of this transformation is the set of all vectors of height n. In other words, the function TA inputs vectors of height n. Similarly, the target or the codomain of TA is the set of vectors of height m. That is the function TA outputs vectors of height m. And the name of this function is a TA. And we use this notation to remind us of the fact that this function was essentially derived from a matrix A. So far, we have seen linear transformations that we get from a matrix A, but can we go in the other direction? In other words, if I start with a transformation from Rn to Rm, when can I guarantee a matrix A such that F is actually the transformation that we get from A? So to find the answer to this problem, we are going to first explore some nice properties that characterize linear transformations. So the first property is that linear transformations send 0 vectors to 0 vectors. The reason for that is that multiplication by a 0 vector gives a 0 vector. And we actually saw an example last time. We saw this example of a translation where this f translates every point in R2 to the right by 1. and we concluded that this f cannot be a linear transformation. And the reason that we actually used was that it took the 0 vector to the vector 1, 0. And that gave us a contradiction. Okay, so now let's look at two very important properties of linear transformations. So if T is a linear transformation from Rn to Rm, then it's going to satisfy these two properties. It's going to preserve addition. In other words, for any two vectors v and w in the domain, T of v plus w will always be equal to T of v plus T of w. And T will preserve scalar multiplication. That is, if v is a vector in the domain and if c is a scalar, then T of CV will always be C times TV. Now, both these properties follow directly from the properties of matrix multiplication. Okay, so let's look at an exercise. We're given this function from R2 to R2, and this takes any vector xy to a vector x squared x plus y, and we have to show that this is not a linear transformation. So observe that if I input my vector 1, 1 into my f, I get 1 squared 1 plus 1, which is just the vector 1, 2. But if I input 2, 2, I get 2 squared and 2 plus 2, which is the vector 4, 4. But we also know that this vector 2, 2 is 2 times the vector 1, 1, but their outputs do not satisfy the same scalar relationship. So the second property that we saw a moment ago is not satisfied, and for that reason this f is not a linear transformation. So we can actually combine the previous two properties into a single property. So if we know that T is a linear transformation from Rn to Rm, we'll say that T preserves linear combinations. So what this means is that if I have k different vectors in the domain and k different scalars, then T of C1 V1 plus C2 V2 through Ck Vk is C1 T of V1 plus C2 T of V2 through Ck T of Vk. So essentially, we first use additivity preservation on this sum. So we get T of C1 V1 plus T of C2 V2 and so on. And then by preservation of scalar multiplication, we pull out the constants and we get this right hand side. So let's look at another exercise. So we are given a linear transformation and we are given that T of 1, 3 is 3 minus 2 and T of 2, 4 is minus 3, 4. And without explicitly knowing what the transformation is, we have to compute T of minus 1, 1. So our strategy is that we first have to write minus 1, 1 as a linear combination of 1, 3 and 2, 4. And then we're going to use the fact that T preserves linear combinations. So first, for unknown coefficients a and b, we set up the equation minus 1, 1 equal to a times the first vector plus b times the second vector. And we actually have to compute these values of a and b, so we can explicitly write this vector minus 1, 1 as a linear combination of the other two. So we take the vector sum, we get a plus 2b and 3a plus 4b, and note that we can rewrite this thing as a product of this matrix with entries 1, 2, 3, 4 and this vector AB. So as a result, this vector AB becomes the inverse of 1, 2, 3, 4 times minus 1, 1. Now the inverse of this matrix is going to be 1 over minus 2 times 4 minus 2 minus 3, 1. You know how to compute the inverses of a 2 by 2 matrix, and then we just multiply. So we get that A has to be 3 and B has to be minus 2. In other words, the linear combination is this. So 3 times the first vector minus 2 times the second vector is minus 1, 1. And then we're going to use the fact that T preserves linear combinations. So T of minus 1, 1 is the same as T of 3 times the first vector minus 2 times the second vector. And that's the same as 3 times t of the first vector minus 2 times t of the second vector. We know what these values are. We plug them in, and then we simplify it to get 15 minus 14. Okay, so before I end this episode, I want to mention this theorem. This theorem says that the following three statements are equivalent. The first statement, of course, being that T is a linear transformation. The second statement being that T preserves addition and scalar multiplication. And the third being that T preserves linear combinations. So if one of them is true, then the other two are true as well, or in other words, they're all equivalent to each other. So if we do have a transformation that preserves linear combinations, then it is a linear transformation. So if it is a linear transformation, how do we find a matrix associated to it? And that's what we're going to learn in the next episode. And with this, I would like to finish this episode. Hopefully things are clear. I will see you guys soon. Up until then, happy learning.